Everything you see around you was once a few simple ingredients. In the first moments after the universe began, just 3 light elements formed the foundation for all of cosmic history. Hydrogen, helium, and a tiny speck of lithium are the primordial fossils from creation's dawn. The quest to understand how they came to be is one of science's greatest detective stories. By the end of this journey, you will have explored 30 astonishing theories that attempt to crack this ancient code. We will venture from the cornerstone model of the Big Bang's first 3 minutes to ideas involving hidden dimensions and decaying phantom particles. Why does the amount of lithium in the cosmos still not match our predictions? Could the fundamental laws of physics have been different back then? The answers redefine our place in the cosmos. What single force do you think could have written the universe's original recipe? The universe was a seething ocean of pure energy. In that first fleeting second, everything was too hot and too dense for matter as we know it to even exist. But as space expanded at a dizzying rate, it also cooled, allowing the first solid particles to condense from the energy sea. Protons and neutrons began to appear, the fundamental building blocks of atomic nuclei. For a brief window, roughly the first 3 minutes of everything, the entire cosmos was a nuclear fusion reactor. Think of it as a cosmic pressure cooker of unimaginable scale. Protons, which are single hydrogen nuclei, tried to stick together, but the universe was still so energetic that these pairs were instantly blasted apart. It was only when things cooled just enough that a proton and a neutron could finally fuse into a stable duo, creating a deuterium nucleus. This was the critical first step. Once deuterium formed, the chain reaction could begin. These deuterium nuclei quickly collided with more protons and neutrons, building up into helium-4, an incredibly stable and tight-knit group of 2 protons and 2 neutrons. This frantic period of cosmic alchemy created nearly all the helium that would ever exist. But just as quickly as it started, it stopped. The universe continued its relentless expansion, becoming too vast and too thin. The particles were now too far apart to collide and fuse anymore. The cosmic pressure cooker had run out of pressure. This entire sequence, known as Big Bang nucleosynthesis, left behind a very specific cosmic fingerprint, a primordial mix of about 75% hydrogen and 25% helium by mass, with only trace amounts of deuterium, helium-3, and lithium. For decades, this model has been the bedrock of our understanding, a triumphant prediction that matches what we observe in the oldest, most untouched corners of space. Yet, this very success hides a deep and puzzling crack in the foundation. What happens when the universe's original recipe, written in the first 3 minutes, does not perfectly match the ingredients we find in the cosmos today? Yet that triumphant model holds a subtle flaw, a cosmic detail that refuses to align. The amount of lithium we actually observe in ancient stars is consistently about 3 times lower than what the classic Big Bang model predicts. This is not a small accounting error. It is a fundamental mismatch, a clue that our story of the first 3 minutes might be incomplete. This discrepancy leads us directly to our second theory, a dramatic reimagining of the universe's infancy. The inhomogeneous Big Bang challenges the very idea of a perfectly smooth beginning. What if the primordial cosmos was not a uniform soup, but was instead lumpy, filled with dense, hot pockets swimming in a sea of thinner, cooler space? In this chaotic landscape, nuclear reactions would not have proceeded at a single, steady rate everywhere. Imagine trying to cook a meal where some parts of your oven are blazing hot while others are barely warm. Your ingredients would cook unevenly, with some burning and others remaining raw. In the early universe, these dense pockets would have been nuclear furnaces, fusing protons into helium with ferocious efficiency. Meanwhile, the more sparse regions would have been far less productive. This uneven cooking would have dramatically altered the final yield of elements, particularly that problematic lithium. In the hottest, densest zones, the frantic nuclear activity could have actually destroyed lithium as quickly as it formed, breaking the fragile nuclei apart. This selective destruction might finally explain why we see so little lithium today. The source of these proposed lumps takes us back to the very beginning, to a concept known as quantum fluctuations. In the first fleeting instance, the empty vacuum of space itself was not truly empty. It was a bubbling, frothing sea where energy flickered in and out of existence. These random, microscopic fluctuations, stretched to cosmic proportions by the universe's rapid inflation, could have seeded all the structure we see today, from galaxies to galaxy clusters. They might also have created the dense patches that forever altered the universe's original elemental recipe. So the very mechanism that gave us a structured cosmos might also be responsible for hiding its primordial lithium. But what if the universe was even stranger before those first protons and neutrons formed? To truly challenge the lithium problem, we must journey back to a time before ordinary matter even existed. Picture a cosmos so incredibly hot and dense that the very components of protons and neutrons, particles called quarks, roamed completely free. This was the quark-gluon plasma, a bizarre primordial soup where quarks and the force-carrying gluons that bind them swirled in a state of unconfined chaos. There were no atoms, no nuclei, not even any individual particles as we recognize them today. Then, in a pivotal cosmic moment, the universe cooled just enough to cross a critical threshold. This was the Quark-Hadron phase transition. In this sudden shift, the free quarks were forever locked together into groups of 2 or 3, forming the first stable protons and neutrons. It was the moment matter as we know it was born from a sea of pure potential. The nature of this transition, however, might be the key to everything. If this change did not happen smoothly and uniformly across the entire cosmos, it could have created profound consequences. Theorists suggest that during this rapid condensation, pockets of space might have ended up with a much higher density of neutrons compared to protons. Visualize a pot of simmering stew as it cools. The ingredients do not always spread out evenly. You might get a chunk of potato here, a dense cluster of meat there. In the early universe, these were neutron-rich chunks. When the nuclear fusion of the first 3 minutes began shortly after, these regions would have followed a completely different recipe. With an overabundance of neutrons available, the chain reaction building helium would have been far more efficient, potentially creating heavier elements on a faster track. This altered pathway could have bypassed the creation of lithium-7 entirely, or more likely, provided the perfect conditions to destroy it shortly after it formed. The phantom lithium we cannot find today may have been erased in these exotic, neutron-dense zones that existed for only a fraction of a second after creation. This overlooked sea of ghostly particles might have been the universe's first great choreographer. Among the frantic particles and searing light of the infant cosmos swam countless neutrinos, so light and weakly interacting that they could pass through a light year of lead without a scratch. This cosmic neutrino background was a relic from the universe's very first second, a fossil even more ancient than the cosmic microwave background. For a brief, critical window, these neutrinos were not just passive spectators. They were active participants in a delicate dance that set the stage for everything to come. Their primary role was in controlling the neutron-to-proton ratio, a single number that would ultimately determine how much of the universe would become helium. In that intensely hot and dense environment, protons and neutrons were constantly transforming into one another. A proton could absorb an electron and turn into a neutron, while a neutron could spit out an electron and become a proton. The rate of this back-and-forth transformation depended entirely on how frequently these particles interacted with the sea of neutrinos and electrons swirling around them. As the universe expanded and cooled, a pivotal moment arrived. The temperature dropped just enough that these transformation reactions became too slow to keep up with the expansion. The constant swapping of identities froze, locking in the neutron-to-proton ratio. From that moment on, the fate of the cosmos was set. The number of neutrons available was the ultimate limiting ingredient for building helium. If neutrinos had been more numerous or interacted just a bit more strongly, they could have tipped the balance, creating a universe with either far more or far less helium than we see today. This is why detecting this primordial neutrino background is one of modern physics' holy grails. Experiments are being designed to catch these faintest of whispers from the dawn of time, not with light-year-thick lead shields, but with ultra-pure, super-cooled crystals that might vibrate with an almost imperceptible energy when a relic neutrino gently interacts. Finding them would give us a direct measurement of the conditions during those first fateful minutes, allowing us to fine-tune our models with precision. It could finally reveal whether these ghostly particles were the silent architects who secretly adjusted the universe's elemental recipe. Those ghostly neutrinos were not the only potential architects of our elemental reality. A far more radical idea suggests the very laws of physics were not written in stone. The variable constants theory proposes that the fundamental numbers governing our universe, like the strength of gravity or the power that binds atomic nuclei, might have been different in that searingly hot, dense past. These are not just arbitrary values, they are the universe's fixed settings, the immutable rules that dictate how everything interacts. The gravitational constant tells matter how strongly to pull on other matter. The fine structure constant controls the strength of electromagnetic interactions, and most crucially for our story, the strong nuclear force determines how tightly protons and neutrons bind together to form atomic nuclei. If any of these numbers were even slightly off, the universe as we know it would not exist. For instance, if the strong force were just a few percent weaker, a single proton could not bind to a neutron to form deuterium, that critical first step in our cosmic chain reaction. Without deuterium, there would be no helium, no heavier elements, and no universe beyond a sea of lonely hydrogen. Conversely, if the strong force was slightly stronger, two protons could fuse together directly, potentially leading to a universe that burned through its nuclear fuel too quickly, leaving behind entirely different elements. The yields of Big Bang nucleosynthesis are exquisitely sensitive to these values. A tiny variation in a constant billions of years ago would have sent the nuclear reactions down a completely different path, creating a final elemental mix that looks nothing like the one we observe. This is where the lithium problem finds a potential solution. If, for just a fleeting moment during the first 3 minutes, the fundamental constants were slightly different, it could have suppressed the specific nuclear reactions that produce lithium-7, while leaving the amounts of hydrogen and helium largely untouched. The implications of this theory are staggering. It hints that the universe may have been fine-tuned for life, not by a divine hand, but through a process of trial and error, or perhaps even a natural evolution of the laws of physics themselves. Were we just incredibly lucky that the numbers landed perfectly for our existence, or is our cosmos one of many, each with its own unique set of rules? Our universe might have been threaded with cosmic scars. These are not scars in space, but scars of space itself, known as cosmic strings. They are theoretical relics, unimaginably thin strands of pure energy left over from the universe's earliest phase transitions, thinner than a single atom yet so dense that a single inch could weigh more than a mountain range. As the cosmos expanded and cooled, its fundamental state shifted, and theorists suggest these shifts could have frozen imperfections into the fabric of reality, just as cracks form in ice as water freezes. These cosmic strings would have been under immense tension, whipping through the primordial plasma at near light speed. Their gravitational influence would have been profound, acting like ultra-dense fishing lines trolling through a sea of particles. They would have pulled ordinary matter, the protons and neutrons known as baryons, into dense wakes behind them. This process could have ripped the smooth, uniform soup of the early universe into a patchwork of extremes. Vast regions would have been left nearly empty, while along the paths of these strings, matter would have piled up into astonishingly dense filaments and knots. In this new vision of the first 3 minutes, the cosmos was not a single, vast pressure cooker. It was a chain of isolated, ultra-intense nuclear reactors, each an island of frantic activity separated by oceans of quiet, sparse space. Within these dense islands, nuclear fusion would have proceeded at a breakneck pace. The overabundance of protons and neutrons in such a small volume would have led to collisions so frequent and violent that the standard chain of reactions could have been dramatically altered. The creation of deuterium and helium might have been turbocharged, but the path to lithium could have been cut short. In these extreme environments, the fragile lithium-7 nucleus, once formed, would have been bombarded by a hail of other particles, shattering it almost instantly. The average elemental mix we calculate for a smooth universe would be completely wrong for this lumpy, string-riddled cosmos. The final recipe we see today would be a diluted average, the result of combining the intense output of these cosmic reaction vessels with the barren outputs of the voids between them. This could elegantly explain why the average lithium count is lower than expected. The universe's first elements may not have been forged in a single, steady fire, but in the brilliant, fleeting flash of countless cosmic forges now lost to time. Another invisible force may have been at work in the cosmic kitchen. The universe's first moments could have generated immense magnetic fields, trillions of times stronger than Earth's, threading the primordial plasma with lines of powerful energy. Picture these fields not as simple bar magnets, but as a dynamic, tangled web of force that filled all of space. Within this web, every charged particle, from the lightest electron to the heavier protons, was not moving freely. Their paths were no longer random. They were forced to spiral along these invisible magnetic field lines, corralled like cattle along cosmic trails. This fundamental change in motion would have directly altered the very heart of nucleosynthesis, the frantic collisions between particles that built the first elements. The rate at which a proton could find and fuse with a neutron to form deuterium, for instance, would depend entirely on how these magnetic fields guided them together or pushed them apart. In some regions, these fields might have focused the particles, increasing their density and supercharging the fusion reactions, creating local pockets rich in helium-3 or deuterium. In other areas, the fields could have acted as a barrier, keeping particles separated and suppressing the formation of these same isotopes. The final cosmic recipe we observe today, a specific blend of hydrogen, helium, and their lighter cousins, would be the average result of this magnetically guided cooking. This theory provides a compelling link to a modern cosmic mystery. We observe powerful magnetic fields woven through galaxies and galaxy clusters today, and their origin has long puzzled scientists. Perhaps these vast fields are not a later development. They could be the diluted, stretched remnants of those primordial magnetic forces, fossils from the first second that have guided the evolution of structure from the smallest atomic nuclei to the largest galaxies. The universe's original elemental fingerprint might have been imprinted by a magnetic hand we are only just beginning to detect. Perhaps the most exotic cooks in the cosmic kitchen were not particles at all, but their heavier, unstable cousins from realms beyond our current physics. The standard model of particle physics is a triumphant catalogue of the universe's known ingredients, but it is almost certainly incomplete. Theories that seek to unify the fundamental forces often predict the existence of exotic, massive particles that were abundant in the extreme heat of the very early universe. These particles would have been incredibly short-lived, decaying out of existence long before the first nuclei ever formed. Yet their death throes could have permanently scarred the cosmic recipe. Imagine a super-saturated solution perfectly still until you drop in a single grain of salt. instantly, crystals begin to form and spread, following a new pattern dictated by that initial grain. In the early universe, these exotic particles were the grains of salt. As they decayed, they could have injected a tremendous burst of energy, photons, or even a flood of extra neutrons directly into the primordial plasma. This sudden injection would have reheated the cosmic soup, but only in certain ways and at a critical moment. The entire delicate balance of the first 3 minutes would have been thrown into chaos. For instance, if a decay released a large number of high-energy photons, it could have broken apart the deuterium nuclei as they were trying to form, creating a bottleneck that slowed down the entire chain reaction leading to helium and lithium. Alternatively, if the decays produced an excess of neutrons, it would have supercharged the reactions that build helium, but also potentially opened up new nuclear pathways that bypassed lithium production entirely. These decaying particle scenarios are like finding an unknown chef's note scribbled in the margin of an ancient recipe. The main instructions for Big Bang nucleosynthesis are correct, but this single, forgotten step changes the final flavor of the dish. The persistent lithium problem, along with other subtle mismatches, could be the direct signature of these phantom particles, a final message from a hidden layer of reality that vanished an instant after the universe began. Einstein's theory of gravity has been the unchallenged rulebook for the cosmos for over a century. But what if that rulebook was subtly rewritten in the universe's first moments? Modified gravity theories propose that the strength of gravity itself was not a constant during that primordial era. Imagine the expansion of the universe as a single dial controlling the cosmic pressure cooker. In our standard story, this dial is set by general relativity, leading to a specific, predictable rate of cooling. But if gravity was stronger back then, the dial would have been turned up. The universe would have expanded faster, racing through its infancy. This frantic pace would have cut the nuclear fusion window brutally short. Protons and neutrons would have been ripped apart before they could complete the full chain of reactions, leaving behind less helium and potentially solving the lithium problem by simply not making as much of it. Conversely, if gravity were weaker, the expansion would have been a slow, languid crawl. The universe would have lingered in its hot, dense state for a much longer time. This extended cooking period would have allowed nuclear fusion to proceed further, potentially converting nearly all the hydrogen into helium and even forging trace amounts of heavier elements. The final elemental abundances are an incredibly sensitive clock, measuring the precise duration of the first 3 minutes. Any deviation from the expected expansion rate leaves a permanent mark on that cosmic fingerprint. The fact that the observed mix of hydrogen and helium fits the standard model so well, with the notable exception of lithium, places incredibly tight constraints on how much gravity could have actually varied. It tells us that if the laws of gravity were different at the dawn of time, they could only have been different by a vanishingly small amount. The primordial elements are therefore not just fossils of the first nuclei, they are a high-precision test, confirming that Einstein's vision of gravity was remarkably accurate almost all the way back to the very beginning. Hidden partners may have danced through the primordial fire. Supersymmetry is a beautiful and elegant theory that suggests every particle we know has a secret twin, a super partner. For every quark, there would be a squark. For every electron, a selectron. These supersymmetric particles would have been incredibly massive and unstable, vanishing in the first frantic moments of the cosmos. Yet the lightest among them, often called the Neutrino, could have been stable enough to survive into the epoch of nucleosynthesis. Think of these neutralinos as phantom guests who arrived too early to the cosmic party and refused to leave. They would have been everywhere in the early universe, a vast, invisible sea of massive particles weaving through the hot plasma of ordinary matter. Their presence would have been felt not through direct collisions, but through their quiet, persistent annihilations. When a neutrino met its anti-particle, they would have destroyed each other in a flash, converting their mass directly into energy, injecting extra heat and radiation into the environment. This would have been like turning up the flame under the cosmic pressure cooker at the worst possible moment. The delicate thermal history of the universe's expansion would have been perturbed. The critical moment when the neutron-to-proton ratio froze, setting the ultimate limit for helium production, would have occurred at a slightly different temperature. A shift of just a few percent could have been enough to alter the final yields of deuterium and that stubborn lithium. Furthermore, the sheer gravitational pull of this unseen sea of massive particles would have subtly altered the expansion rate of the universe during those first 3 minutes. A slower expansion gives nuclei more time to collide and fuse, while a faster expansion cuts the process short. The lightest supersymmetric particles, therefore, could have tweaked the cosmic recipe in 2 ways at once, by adding extra heat and by warping the expansion of space itself. This dual influence makes them a prime candidate for solving the lithium discrepancy. The amount of lithium we see today could be the precise signature of these phantom particles, a final clue that our universe is not just made of the matter we see, but is also shaped by the ghostly echoes of its symmetrical past. The very existence of matter is a cosmic mystery. Why is the universe made of something rather than nothing? After the Big Bang, equal amounts of matter and antimatter should have been created, destined to meet and annihilate in a final flash of light, leaving behind a barren cosmos of pure radiation. The fact that we are here means this perfect symmetry was broken. A mechanism called Baryogenesis must have tipped the scales, creating a tiny, 1 in a billion excess of matter over antimatter. The Affleck-Dine mechanism offers one of the most elegant solutions. It proposes that in the universe's first moments, a special kind of field, related to the fundamental forces that govern quarks and leptons, began to oscillate like a spring set in motion. As this field swung back and forth, it stored immense energy. When it finally decayed, it did not decay symmetrically. It released its energy preferentially, dumping a vast surplus of quarks over antiquarks into the newborn cosmos. This was the moment matter was born from an almost nothingness, but this process did not happen uniformly. The oscillations of this field could have been chaotic, creating regions where the field was more energetic and others where it was less so. When it decayed, this patchwork of energy translated directly into a lumpy distribution of matter. Some areas of the primordial plasma became incredibly dense with protons and neutrons, while adjacent regions were left almost barren. This is the critical link to our elemental story. The nuclear fusion of the first 3 minutes did not begin with a smooth, even mixture. It started in a cosmos already imprinted with profound density variations, a direct consequence of how matter itself was created. In the ultra-dense patches, nuclear reactions would have roared to life with ferocious intensity. The frantic collisions would have rapidly built up helium, but they also would have provided a hostile environment for the fragile lithium-7 nucleus, shattering it under a hail of other particles. Meanwhile, in the sparser regions, the reactions would have sputtered, producing a different mix of elements. The final cosmic recipe we observe today, especially the curiously low average amount of lithium, could be the diluted result of combining these wildly different outputs. The Affleck-Dine mechanism suggests that the fingerprint of the first elements is not just a record of nuclear physics, but a direct echo of the violent, asymmetric birth of matter itself. The universe may not have been born from a single, explosive beginning. A radical alternative rewrites the entire origin story, suggesting our cosmos is just one act in an endless cyclical drama. This is the ekpyrotic universe model, or the cyclic model. It proposes that our three-dimensional universe exists as a membrane or brain floating within a higher dimensional space. Think of our reality as a single, immense sheet of paper suspended in a vast, unseen void. Another brain, another cosmic sheet, floats parallel to our own. In this model, the Big Bang was not the moment of creation from nothing. It was the violent, transformative result of a collision between our brain and its neighbor. The intense heat and density we attribute to the universe's birth were instead generated by this monumental impact. This collision set our cosmic cycle in motion, leading to the expanding universe we observe today. But what happens before the bang in this story? The universe enters a long, slow contracting phase. It does not start from an infinitely hot, dense singularity. Instead, it begins from a cold, sparse, and nearly empty state that gradually contracts and heats up until the moment of the brain collision, which we call the Big Bang. This pre-bang history has profound consequences for the first elements. The initial conditions for nucleosynthesis are completely reset. The classic Big Bang model has two famous puzzles, the horizon problem and the flatness problem. The horizon problem asks why the universe is so uniform, as regions now far apart appear to have been in contact long ago. The flatness problem questions why the geometry of the universe is so perfectly balanced between eternal expansion and eventual collapse. In the standard story, a period of rapid inflation is invoked to solve these issues. But in the ekpyrotic model, the long, slow contraction before the bang naturally smooths and flattens the universe, solving these problems without the need for a separate inflationary epoch. This different path to a smooth cosmos means the nuclear reactions of the first 3 minutes could have unfolded in a subtly altered environment. The thermal history, the rate of cooling, and the exact moment when particles decoupled could all have been different. A universe that contracts and then bounces has a different rhythm than one that simply explodes and expands. This altered rhythm would have directly affected the neutron to proton freeze out and the duration of the nuclear fusion window. The final mix of hydrogen, helium, and lithium would bear the signature of this cosmic bounce rather than a pure explosion. The persistent lithium discrepancy might find its resolution here, not by tweaking the physics within our universe, but by completely reimagining the events that preceded it. The elements we see today could be fossils not of a single creation, but of the latest in an infinite series of cosmic rebirths. String theory paints a picture of existence before the Big Bang that challenges our deepest intuitions. It envisions a pre-bang epoch governed not by the geometry of space we know, but by a fundamental field called the dilaton. This field acted as a cosmic master dial, controlling the strength of all physical interactions. In this primordial era, the dilaton was not constant. Its value was plummeting, causing gravity and the other forces to grow exponentially weaker as time ticked backward toward the moment of the bang. This led to a phenomenon known as superinflation, a period of hyper-accelerated expansion that was even more extreme than the standard cosmic inflation most theories describe. The entire universe was stretched and smoothed to an incredible degree, but it was also left in a state of profound cold and emptiness. The cosmos was a vast, frigid, and nearly static void. Then came the bounce. The dilaton field reached a critical point and rebounded, its energy converting violently into the searing heat and dense matter we recognize as the Big Bang. This transition from a cold, empty, contracting phase to a hot, dense, expanding one completely resets the initial conditions for creating the first elements. The thermal history of the universe was turned upside down. Nucleosynthesis did not begin from an infinitely hot singularity. It started from a specific, finite temperature that was a direct result of this cosmic bounce. The entire timeline of the first 3 minutes, the critical window for nuclear fusion, would have been fundamentally different. The cooling rate would have been altered, changing the precise moment when the neutron-to-proton ratio froze. The duration of the nuclear fusion window itself might have been longer or shorter. Every single variable that goes into calculating the final mix of hydrogen, helium, and lithium would be subject to new rules written by the dilaton. This means the primordial abundances predicted by standard Big Bang nucleosynthesis could be completely rewritten. the universe might have produced a dramatically different blend of light elements, one that could naturally account for the lithium problem or even point to abundances we have not yet thought to look for. The elements we see today would then be a fossil not of a singular beginning but of a great cosmic turning point, a bounce from a cold, pre-existing state into the fiery universe we call home. The primordial chaos might have been filled with cosmic traps. These were not traps of matter, but of pure gravity, microscopic knots in space-time known as primordial black holes. Theorists suggest that in the universe's first violent instance, extreme density fluctuations could have collapsed directly into black holes, some no larger than a single atom yet containing the mass of a mountain. For eons, these tiny, dark objects would have drifted through the expanding cosmos, silently consuming any matter that wandered too close, but they were not eternal. Through a process known as Hawking radiation, these black holes would have slowly evaporated, losing mass over astronomical timescales until they reached a critical point and vanished in a final, violent burst of energy. The smallest of these black holes would have lived the shortest lives, exploding like a countless series of miniature cosmic bombs during the very epoch of nucleosynthesis. Each detonation would have been a flashpoint of unimaginable energy, releasing a torrent of high-energy gamma rays, particles, and antiparticles directly into the surrounding primordial plasma. This was not a gentle addition of heat. It was a series of localized cataclysms that fundamentally reshuffled the elemental deck. The furious radiation from these evaporating black holes would have acted like a cosmic sledgehammer, striking the newly formed atomic nuclei and blasting them apart. This process, called photodisintegration, would have reversed the work of fusion, shattering fragile deuterium and lithium back into their constituent protons and neutrons. In some regions, this could have created a nuclear wasteland, erasing the delicate products of the first 3 minutes. Yet in the chaotic aftermath, it also could have sparked a secondary wave of nucleosynthesis. The flood of newly freed neutrons and the intense energy could have driven different, more exotic nuclear reactions, potentially forging rare isotopes like lithium-6 or extra helium-3 in pockets of space. The final elemental mix we observe today would then be a complex palimpsest, the result of the standard Big Bang recipe being partially erased and then rewritten by the fiery death throes of these primordial ghosts. The missing lithium might not be a shortage at all, but the signature of its systematic destruction in the flash of a billion tiny explosions. These ghostly particles had one more quantum trick to play. Neutrinos are not one single entity but come in 3 distinct flavors: the electron neutrino, the muon neutrino, and the tau neutrino. In the vacuum of empty space, a bizarre quantum phenomenon occurs. A neutrino born as one flavor does not remain that way. It oscillates, seamlessly transforming into another flavor as it travels, a constant, silent identity crisis written into the fabric of reality. During the frantic first seconds of nucleosynthesis, this oscillation was not a slow, meandering process. It was a rapid-fire dance, a desperate struggle for equilibrium in an impossibly dense and hot environment. The entire plasma was so thick with particles that neutrinos could not travel even a minuscule distance without colliding with something, constantly being measured and forced back into a definite flavor state. This frantic back and forth was not just a sideshow. It was a critical part of the cosmic energy budget. Each time a neutrino oscillated, it required a tiny amount of energy, and the different flavors interacted with the surrounding plasma in subtly different ways. The electron neutrino, in particular, held a special power. It was the only one directly involved in the reactions that transformed neutrons into protons and back again, the very reactions that set the neutron-to-proton ratio. If the oscillations between flavors were efficient enough, they could have acted as a cosmic energy sink, subtly cooling the neutrino sea relative to the rest of the plasma. This tiny thermal shift would have occurred at the most pivotal moment, just as the universe was cooling to the point where the neutron-proton transformations were about to freeze. A slightly different temperature at that exact instant would have locked in a different final number of neutrons, changing the ultimate amount of helium produced. The universe's original helium abundance is therefore a cosmic stopwatch, recording the precise conditions of the neutrino bath during those first 2 seconds. Even a minuscule alteration in the rate or nature of those early oscillations would leave a permanent, detectable mark on the cosmos. This is why scientists now use the observed amounts of primordial helium and deuterium as a high-precision tool. These light elements are not just fossils, they are a time machine. By measuring their ratios with exquisite care in the oldest clouds of gas, we can effectively look back and constrain the physics of neutrinos from a time long before the first star ever shone. The recipe for the first elements is now being used to interrogate the quantum rules that govern the universe's most elusive particles. Some supersymmetric particles were so aloof they barely interacted with our world at all. The gravitino, the hypothetical superpartner of the graviton, was the ultimate ghost in the cosmic machine. Its interactions were not just weak, they were super weak, mediated only by the feeblest of forces, gravity itself. This profound detachment gave it an astonishingly long lifetime, allowing it to persist long after other exotic particles had vanished, while most of the primordial chaos settled into the familiar rhythm of nucleosynthesis. A sea of these gravitinos drifted through the newborn elements, utterly indifferent. Their decay was not a matter of if, but when, and that when was the problem. If these particles survived into or even just beyond the epoch of Big Bang nucleosynthesis, their eventual decay would have been catastrophic. Each gravitino would have vanished in a flash, releasing a tremendous burst of high-energy radiation directly into the cosmos. This was not a gentle addition of heat. It was a series of targeted strikes on the universe's first atomic nuclei. The gamma rays produced in these decays would have had more than enough energy to blast apart the delicate bonds holding deuterium, helium, and lithium together. A process known as photodisintegration would have run in reverse, shattering the very elements that had just finished forming. The universe's hard-won elemental recipe would have been torn to shreds after the cosmic kitchen had already closed. This is the heart of the gravitino problem. The successful predictions of Big Bang nucleosynthesis for the abundances of hydrogen, helium, and deuterium are so precise that they leave almost no room for such a disruptive event. The fact that we see the expected amounts of these elements today places incredibly tight constraints on the possible properties of the gravitino and other super-weakly interacting particles. Their lifetime, their mass, and their initial density are all forced into a narrow window by the pristine fingerprint of the light elements. If they existed in any significant number, they could not have lived long enough to ruin the cosmic abundances we observe. This turns cosmology into a powerful tool for particle physics. The existence of these elusive particles is not just a question for powerful colliders. It is a question that can be answered by looking at the oldest stars and the most ancient clouds of gas. The gravitino problem tells us that any viable theory of supersymmetry must include a mechanism to safely remove these dangerous relics before they can destroy the universe's first and most important creations. Gravity itself might have been leaking into hidden dimensions. Our universe could be a vast, three-dimensional membrane adrift in a higher dimensional space, a concept known as the brain world. In this extraordinary picture, the fundamental forces of nature, like electromagnetism and the nuclear forces, are trapped on our brain. They cannot escape. But gravity is different. It is the geometry of space-time itself, and as such it can seep out into the bulk, the unseen dimensions that surround us. This leakage would have had a dramatic effect during the universe's first few minutes. The expansion rate of the cosmos is governed by the strength of gravity and the density of energy. If gravity was seeping away into extra dimensions, it would have effectively weakened its grip on our own brain. To achieve the same observed rate of expansion, the universe would have needed to be filled with far more energy density than we currently account for. During the radiation-dominated era of Big Bang nucleosynthesis, this would have fundamentally altered the cosmic clock. The expansion of space would have proceeded at a different rhythm, faster or slower depending on the exact model. Think of it like trying to bake a cake while the oven's thermostat is miscalibrated. The ingredients are the same, but the cooking time is completely wrong. In the cosmic kitchen, the duration of the first 3 minutes was everything. A faster expansion rate driven by this gravitational leakage would have rushed the universe through its nuclear fusion window. Protons and neutrons would have been separated before they could complete the full chain of reactions, leaving behind less helium and lithium. A slower expansion, conversely, would have given the particles more time to collide and fuse, potentially converting more hydrogen into helium and creating a different blend of trace elements. The delicate balance we observe today, the precise ratios of hydrogen, helium, and deuterium, acts as a powerful stopwatch that measured the expansion rate billions of years ago. The fact that the standard Big Bang model fits so well tells us that gravity could not have leaked too much. But the persistent lithium problem leaves just enough room to wonder if a tiny, almost imperceptible amount of this leakage occurred, subtly tweaking the cosmic clock and leaving its signature in the missing lithium. The first elements may be our first real evidence that our universe is not all there is. Even the speed of light may not have been a constant. This is the audacious claim of varying speed of light cosmology, a theory that dares to rewrite one of physics' most sacred rules. In our modern universe, the speed of light is the universe's ultimate speed limit, a fixed constant that underpins everything from Einstein's relativity to our understanding of causality. But what if, in the first unimaginable moments, light raced across the newborn cosmos at a pace trillions of times faster than it does today? Such a radical change would effortlessly solve one of cosmology's great puzzles, the horizon problem. This is the mystery of why the universe looks the same in all directions, even though regions now on opposite sides of the sky could never have been in thermal contact if light had always traveled at its current speed. A faster speed of light in the early universe would have allowed these distant regions to communicate, to exchange energy and homogenize their temperature, creating the stunning uniformity we see in the cosmic microwave background. But this solution comes with cosmic consequences that reach deep into the nuclear forge of the first elements. The speed of light is not just a number for travel. It is woven into the fundamental constants that govern the strength of nuclear forces, specifically the fine structure constant, which controls the electromagnetic force that holds atoms together and dictates how atomic nuclei interact, is directly proportional to the square of the speed of light. If the speed of light was higher back then, the fine structure constant would have been vastly different. This single change would have recalibrated the entire nuclear physics of the early universe. The cross-sections of nuclear reactions, which are the effective target areas that determine how likely particles are to collide and fuse, are exquisitely sensitive to this constant. A different fine structure constant would mean protons and neutrons would have interacted with each other in completely new ways. The probability of two protons overcoming their mutual electromagnetic repulsion to get close enough for the strong nuclear force to take over would have been altered. The stability of the deuterium nucleus, that crucial first stepping stone, could have been enhanced or diminished. The entire carefully choreographed chain of reactions that builds helium and lithium would have been thrown into disarray following a new, unknown sequence. The final elemental abundances predicted by a universe with a variable speed of light could be dramatically different from the standard model. The persistent lithium problem might simply vanish, not because of a late-stage destruction process, but because the universe's original nuclear physics, governed by a different set of constants, never produced as much lithium in the first place. This theory suggests that the cosmic recipe for the first elements was written with a pen that faded over time, its ink the very speed of light itself. Perhaps the lithium shortage is not a problem to be solved, but a profound clue to our own existence. Beyond the physical mechanisms lies a philosophical perspective that reframes the entire cosmic question. This is the anthropic principle, a simple yet staggering idea. It suggests that the fundamental constants and initial conditions of our universe appear finely tuned because only in such a universe could observers like us ever arise to notice them. The specific abundances of the light elements are not a random outcome. They are a necessary line in a cosmic recipe that had to be followed precisely for life to become possible billions of years later. Consider the amount of helium, fixed at almost exactly 25% by mass. If the nuclear forces had been slightly weaker, or the universe had expanded just a bit faster, far less helium would have been forged. A universe with significantly less helium would have led to profoundly different first stars. These stars would have burned their fuel differently, lived shorter lives, and failed to produce the heavy elements like carbon and oxygen that are the bedrock of life. Conversely, a universe with too much helium would have created overly massive, short-lived stars that bathed their planetary systems in lethal radiation, sterilizing any potential cradle of life before it could form. The golden window for helium was remarkably narrow. The fact that we measure a value so perfectly poised within that window forces us to confront a remarkable possibility. We do not observe a universe with odd or unlivable elemental abundances precisely because we are here to observe it. Our very existence as conscious beings built from stardust selects for the one cosmic history that could have produced us. The puzzling lithium discrepancy itself might be part of this selection. While 3 times less than predicted, it is not zero. That trace amount was still essential, playing a role in the nuclear chemistry of later generations of stars that enriched the cosmos with the elements for planets and people. The anthropic principle does not invoke a creator. Instead, it presents a cosmic filter. Countless universes may have been born with different laws and different elemental recipes, but the vast majority of them would be barren, silent, and devoid of anyone to ponder the first 3 minutes. We find ourselves in the one that worked, a universe whose original elemental fingerprint was the first and most important signature on the contract for life. The very fabric of space and time might be a grand illusion. The holographic principle, one of the most radical ideas in physics, suggests that our 3-dimensional universe, with all its stars, galaxies, and history, could be a projection of information encoded on a distant 2-dimensional surface. Think of the immersive world of a hologram on your credit card. The image appears to have depth and volume, but all its information is stored on a flat, shimmering sheet. Now imagine our entire cosmos as that kind of projection. This is not merely a metaphor for the large-scale universe. It implies that in its earliest, most energetic moments, the universe was fundamentally 2-dimensional. The seething quark-gluon plasma and the frantic nuclear reactions of the first 3 minutes were not happening in a volume of space as we understand it. They were a computation, a complex interplay of data on a cosmic boundary we cannot see. This rethinking of reality's basic structure forces us to reconsider the nuclear physics that forged the first elements. In a holographic universe, the very concepts of locality and distance break down at the most fundamental level. 2 protons fusing in the primordial fire might not have been 2 separate particles colliding in a shared space. They could have been linked from the start, their interaction predetermined by entangled information on the boundary. The probabilities of nuclear reactions, the cross-sections that dictate how often particles fused, might not have been governed by the classic laws of 3-dimensional physics alone. They could have been emergent properties of a deeper, information-based reality. The precise yields of hydrogen, helium, and lithium would then be a cosmic printout, the result of a calculation performed on a 2-dimensional screen. The persistent lithium discrepancy could be a rounding error in that calculation, a subtle clue that we are still using the wrong physics to interpret a cosmic hologram. If the first elements are projections, then their abundances are not just fossils of a nuclear age. They are a message, a literal cosmic code written in the language of hydrogen and helium, waiting to be deciphered from a dimension we have not yet learned to see. Strings were the universe's original fundamental ingredients, before particles, before nuclei, even before the dimensions of space were fixed. The cosmos was a dense, hot gas of these vibrating, one-dimensional loops of energy. This is the vision of string gas cosmology, a model that reimagines the Big Bang not as a singular point, but as a phase transition from a chaotic, multi-dimensional stringy soup. The behavior of these strings is governed by a unique property. In a universe with all its spatial dimensions compact and curled up on themselves, strings can wind around these tiny circles. They become trapped, unable to move freely, and this winding energy dominates the cosmos, creating a stable, hot, and nearly static phase. The universe was not expanding. It was held in a tense thermal equilibrium by a tangled web of wound-up strings. Then came the great unwinding. Through a process involving the collision of these winding modes, the universe found a way to escape its own confinement. Three of the spatial dimensions were suddenly allowed to decompactify and expand rapidly, while the remaining dimensions stayed tightly curled, too small for us to ever perceive. In that explosive moment of unwinding, the pent-up energy stored in the strings was released in a cataclysmic flash. This was not an explosion from a point of infinite density. It was the violent unfurling of space itself, and it filled the newborn three-dimensional universe with a blistering, uniform bath of radiation. This single event set the thermal stage for everything to come. The entire thermal history of the universe was reset from the ground up. The starting temperature, the initial density, and the very rate of expansion were all direct consequences of this stringy, unwinding process. This means the clock for Big Bang nucleosynthesis started ticking under conditions that were fundamentally different from those in the standard model. The window for nuclear fusion would have opened at a different temperature. The moment when the neutron-to-proton ratio froze would have occurred at a slightly different time. Every single step in the chain reaction that built the first light elements was now subject to the unique rhythm dictated by the thermodynamics of strings. The final mix of hydrogen, helium, and lithium would bear the signature of this cosmic release of tension. The persistent lithium problem could find a natural resolution here, not by adding or destroying particles, but because the universe's nuclear kitchen was preheated by a different kind of fire altogether. The elements we see today may be the permanent echo of the moment when the strings of the cosmos finally unwound, setting three dimensions free to build a world. The mathematics that built our universe might have been fundamentally different at the start. Non-commutative geometry is a framework that suggests the very coordinates of spacetime did not commute in the primordial fire. What does that mean? In our everyday world, the order in which you do things does not always matter. You can walk 5 steps north, then 5 steps east, and you will end up in the same spot as if you had walked east first and then north. The operations commute, but in the quantum realm, this simple logic breaks down. In the first instance, the fabric of reality might have been so jumbled that moving in one direction and then another did not yield the same result as moving in the reverse order. This points to a deep, fundamental granularity, a quantum foam where spacetime itself was a churning, uncertain froth. This was not just empty space. It was a dynamic, pixelated landscape where the very concept of a smooth, continuous path ceased to exist. In such an environment, the behavior of the particles trying to form the first nuclei would have been profoundly altered. Their interactions were no longer happening on a smooth stage, but on a bumpy, turbulent quantum surface. This granularity would have introduced subtle corrections to the rates at which particles scattered and fused. Think of trying to play a game of billiards on a perfectly smooth felt table versus a table that is covered in a fine, chaotic grit. The path of the balls, the angles of their collisions, and the final outcome would be unpredictably different. In the cosmic context, this grit was the non-commutative structure of spacetime. The probability of a proton successfully colliding with a neutron to form deuterium, that all-important first step, could have been slightly enhanced or suppressed. The entire network of nuclear reactions that we meticulously calculate for Big Bang nucleosynthesis was playing by a subtly different set of rules written for a fuzzy, pixelated cosmos. The final yield of elements, particularly the fragile lithium-7, would bear the signature of this early granularity. The lithium we cannot account for might be missing because the quantum foam of the infant universe provided a rougher road for its creation, a tiny mathematical correction that echoed for billions of years. The redshift of distant galaxies is the bedrock of modern cosmology. We see their light stretched toward the red end of the spectrum and interpret this as a Doppler effect, the signature of a universe flying apart from a central point. This single observation is the primary evidence for the Big Bang and the expanding cosmos that sets the stage for Big Bang nucleosynthesis. But what if that interpretation is wrong? Theory 23 dares to ask this heretical question. The tired light hypothesis offers a radical alternative. It proposes that the redshift is not caused by the stretching of space itself, but by a simple, gradual loss of energy as light travels across the vast cosmic voids. In this view, a photon of light over millions of light years gets tired. It interacts ever so slightly with the sparse material or even the fabric of space in a way that saps its energy, causing its wavelength to lengthen and shift to the red. This is not an expansion of the universe, but a process happening within a static, eternal cosmos. The implications for our story of the first elements are nothing short of revolutionary. If the universe is not expanding, then the entire timeline of the Big Bang unravels. There was no initial hot, dense state. There was no cosmic pressure cooker that existed for only 3 minutes. The entire rationale for Big Bang nucleosynthesis, with its frantic burst of fusion in a rapidly cooling and thinning plasma, simply vanishes. In a static universe, the light elements could not have been forged in a single primordial event. Their origin story must be completely rewritten. Perhaps they were synthesized slowly and steadily over eons inside the first generations of stars, or in some other, more exotic process we have yet to conceive. The specific mix of 75% hydrogen and 25% helium, which the standard model so elegantly predicts, becomes a monumental coincidence in a tired light cosmos, a puzzle with no clear solution. While most cosmologists dismiss tired light due to other evidence, like the precise blackbody spectrum of the cosmic microwave background, the theory forces a profound reflection. Our entire understanding of the universe's first 3 minutes and the origin of every atom in our bodies rests entirely on our interpretation of that faint red glow from the depths of space. Gravity may not have been the universe's primary architect. Another force far more potent in our everyday lives could have written the original recipe. Welcome to the plasma universe, a vision of cosmos where immense electric currents and searing electromagnetic fields take center stage, demoting gravity to a mere spectator. In this controversial narrative, there was no initial singularity, no hot Big Bang. Instead, the universe has always existed as an endless sea of plasma, a fourth state of matter where atoms are ripped apart into a soup of free electrons and atomic nuclei. Within this eternal, dynamic medium, vast instabilities can arise. Think of the entire cosmos as a flickering cosmic neon sign, scaled up to an unimaginable degree. These instabilities create powerful double layers, regions of intense electric charge separation that can accelerate particles to nearly the speed of light. When these relativistic particles slam into each other or into denser regions of plasma, Their violent collisions can forge atomic nuclei directly, a process entirely distinct from the gentle simmering of thermonuclear fusion. This is not a slow, temperature-dependent cooking process. It is a violent electric alchemy. Supporters of this electric cosmology point directly to the cosmic abundances themselves as proof. They argue that the observed ratios of light elements, particularly the amounts of helium-3 and deuterium, are better explained by the nuclear pathways available in high-energy plasma interactions than by the traditional Big Bang model. The stubborn lithium problem, they suggest, simply vanishes when you abandon the idea of a singular, hot beginning and embrace a universe perpetually powered by electricity. This is a cosmos without a definitive start, where the first elements were not forged in a single flash, but are continuously born and reborn in the brilliant, twisting filaments of cosmic power that light up the void. The Big Bang was not the only possible beginning. For decades, it faced a formidable and elegant challenger, a model of the cosmos that rejected a fiery origin in favor of eternal sameness. The steady-state theory proposed a universe with no beginning and no end, forever expanding yet paradoxically remaining unchanged in its overall appearance. To achieve this cosmic magic trick, it required one extraordinary mechanism: the continuous creation of matter. Out of the void, new hydrogen atoms would slowly but steadily pop into existence, just enough to fill the gaps left by the expansion and maintain a constant density throughout all of time. This single, radical idea completely rewrites the story of the first elements. In the Big Bang narrative, the light elements are primordial fossils, a one-time, only product of a unique, hot, dense phase. But in a steady-state cosmos, there is no primordial event. The universe has always looked roughly as it does now, and the hydrogen and helium we see must have been produced continuously, not in a single flash. This demands an entirely different factory for the elements. The primary candidate was, and still is, the stars themselves. In this eternal universe, generations of stars will be constantly forming, living, and dying, fusing hydrogen into helium in their cores, and then scattering these newly forged elements back into space when they exploded. The cosmic mix of elements would not be a relic from a creation event, but a snapshot of an ongoing, infinite cycle of stellar birth and death. The observed abundance of helium, about 25%, becomes a puzzle of a different kind. It would represent a balance, an equilibrium between the rate at which stars produce helium and the rate at which the universe expands and dilutes it. This model elegantly sidestepped the lithium problem altogether because there was no specific prediction for a primordial lithium abundance. Its presence was just part of the ongoing chemical evolution of the cosmos. While most evidence, most notably the cosmic microwave background, ultimately supported the Big Bang, the steady-state theory remains a brilliant testament to scientific imagination. It forces us to ask a deeper question. Are the first elements a unique signature from a moment of creation, or are they simply the steady, timeless output of a universe that has always been, and always will be, hard at work? The singularity at the Big Bang was not an end, but a cosmic turning point. Loop quantum cosmology rewrites the ultimate origin story by applying the rules of quantum physics to space and time themselves. In this view, the universe cannot be crushed into an infinitely dense point. There is a fundamental limit, a smallest possible size for the fabric of reality. Before our expanding universe began, there was a great cosmic contraction. A previous phase of reality was collapsing in on itself, growing hotter and denser, but as it approached that fundamental quantum size, a repulsive force generated by the quantum nature of gravity kicked in. Instead of a catastrophic singularity, the universe bounced. It rebounded like a cosmic spring, and that rebound is what we experience as the Big Bang. This big bounce completely resets the initial conditions for everything that follows. The universe our nucleosynthesis models described did not emerge from an unknowable, infinitely hot state. It was born from a specific, finite density and temperature dictated by the quantum geometry of the bounce itself. This means the thermal history of the cosmos was different from the very first moment. The rate at which the universe expanded and cooled after the bounce was governed by quantum-corrected equations. The all-important neutron-to-proton ratio, which freezes within the first second, would have been set during this quantum gravitational dawn. A slightly different expansion rhythm would have meant a different number of neutrons available when the nuclear fusion window opened. The entire 3-minute chain reaction from the first deuterium bonds to the final lithium nuclei would have proceeded on a new schedule. The precise yields of the light elements become a direct test of this quantum bounce. The stubborn lithium discrepancy could be the faint but persistent echo of that repulsive quantum force, a signature that our universe remembers its previous contraction. The first elements are not just relics of a fiery beginning, but permanent records of the moment gravity itself became quantum and turned collapse into creation. A hidden mirror universe could be silently shaping our own. This is the theory of mirror matter and hidden sectors, a concept that posits a complete parallel cosmos made of particles that are perfect reflections of our own. Every electron, every quark, every force-carrying particle in our reality would have a twin in this mirror world. Yet these two realms are almost entirely separate, communicating with one another only through the faint, universal whisper of gravity. In the fiery dawn of our cosmos, this mirror sector would have experienced its own Big Bang, its own rapid expansion, and its own frantic epoch of nucleosynthesis. It would have cooked up its own primordial mix of hydrogen and helium, following the same nuclear physics but potentially under slightly different conditions. The temperature of the mirror universe at any given moment, or the exact timing of its key transitions, might have been offset from ours by just a fraction. This tiny difference would have been enough to send its elemental cooking down a subtly different path. The final recipe for the light elements that we measure in our universe would then not be a pure signal from our own past. It would be a blended average, a cosmic cocktail mixed from the output of two separate nuclear forges. The mirror sector's contribution, flowing into ours only through gravity, would dilute the primordial abundances we expect from our single-sector models. This elegant blending could finally explain certain cosmological anomalies, most notably the curious case of the missing lithium. The amount of lithium-7 predicted by standard Big Bang nucleosynthesis is what our sector should have produced alone. But if a mirror sector contributed a flood of extra hydrogen and helium without a corresponding amount of lithium, the overall average we observe would be skewed, showing the exact lithium deficit that has puzzled scientists for decades. The elements we once thought were pure fossils from our creation may instead be the combined signature of two intertwined realities, one visible and one forever hidden in plain sight. The faint afterglow of creation holds a secret. The cosmic microwave background is more than just a baby picture of the universe. Its perfect blackbody spectrum is a pristine fossil, a thermal echo of a time when the cosmos was a smooth, hot plasma. Any violent event that injected energy into this calm sea would have left a permanent scar, a subtle distortion in that perfect thermal curve. The theories we have explored are not just abstract ideas. They are potential histories, each of which would have written its own signature into this ancient light. Consider the decay of a gravitino or the explosion of a primordial black hole. Such events would have unleashed torrents of high-energy photons long after the first nuclei formed. These photons would not have simply warmed the cosmos. They would have fundamentally reshuffled the way energy was distributed among the existing particles, pushing the blackbody spectrum out of its perfect equilibrium. One type of distortion is known as a Compton Y distortion. It occurs when hot, energetic electrons scatter the photons of the CMB, giving them a slight energy boost. This creates a specific telltale dip in the spectrum's intensity at certain wavelengths and a rise at others. Another type is a chemical potential distortion, or a mu distortion, which arises when energy is dumped into the universe so early that full thermal equilibrium cannot be restored. Each exotic process leaves a unique fingerprint. A specific form of decaying dark matter would produce one pattern of distortion. The evaporation of a population of tiny black holes would produce another. The hunt for these spectral scars is now a primary goal of next-generation cosmology. Future space missions are being designed with the exquisite sensitivity required to detect these minuscule deviations. They are not just looking for a signal, they are trying to read a cosmic police line-up, comparing the fingerprints left by various theoretical suspects against the pristine background. Finding a specific distortion could immediately validate one of our 30 theories and rule out a dozen others. The origin of the first elements and the fate of the universe's missing lithium may ultimately be decided not by looking at ancient stars, but by reading the faintest wrinkles in the universe's first light. Our cosmic crime scene has been contaminated. The pristine fingerprint of the first elements has been smudged by billions of years of stellar activity. The ancient clouds of gas we observe are not perfectly preserved time capsules. They are archives that have been repeatedly edited and rewritten by a process known as astration. This is the continuous cosmic recycling where interstellar gas collapses to form stars, which then fuse lighter elements into heavier ones in their cores. When these stars die, they explode or shed their outer layers, spewing this newly forged material back into space, enriching the surrounding gas clouds. The next generation of stars then forms from this polluted material, beginning the cycle anew. Imagine trying to analyze the original recipe for a classic dish, but every time you taste it, the chef has added a new spice or substituted an ingredient. The original flavor is still there, but it is now layered with countless later additions. This is the challenge astronomers face. The lithium we measure in the oldest stars is not necessarily the pure lithium from the first 3 minutes. It is a mixture potentially contaminated by lithium produced in later cosmic events, like cosmic ray spallation, where high-energy particles smash into heavier nuclei and break them apart, creating lighter elements like lithium-6, or even by material ejected from certain types of aging stars. To test our 30 theories, we must find a way to peel back these layers of galactic pollution and glimpse the true primordial signature. Astronomers act as cosmic detectives, using sophisticated tools to separate the signal from the noise. They search for the most ancient metal-poor stars. In astronomy, metals refer to any element heavier than helium. A star with very low metal content likely formed from gas that had undergone very little astration, making it a cleaner window to the past. By measuring the correlation between lithium abundance and iron content in thousands of these ancient stars, they can extrapolate back to what the lithium level would have been when the interstellar gas was completely pristine, before the first polluting stars had even died. This painstaking forensic work reveals a stubborn truth. Even when we correct for this contamination, the primordial lithium problem persists. The amount of lithium-7 in the most pristine environments is still about 3 times lower than the standard Big Bang model predicts. This realization is as profound as it is humbling. It tells us that the discrepancy is not an artifact of our messy, evolved galaxy. It is a fundamental feature of the cosmos, a true anomaly imprinted at the very beginning. The contamination of astration does not solve the mystery. It instead forces us to refine our search, proving that the answer must lie not in our galactic backyard, but in the physics of the universe's first fleeting moments. The final clues to this cosmic mystery are now being actively hunted. Across the globe and in the vacuum of space, a new generation of scientific instruments is coming online, designed with the power to test our 30 theories directly. These are not passive observatories, they are time machines and forensic labs built to dissect the faintest whispers from the dawn of time. The James Webb Space Telescope is peering into the era of the very first galaxies, studying their ancient light to measure the primordial elemental abundances in environments untouched by later stellar pollution. It searches for the chemical fingerprint of that first 3 minutes in the most pristine gas clouds the universe has left. Meanwhile, on the ground, a monumental project known as SYMBIOS-4 is preparing to map the cosmic microwave background with a sensitivity we have never before possessed. Its arrays of ultra-sensitive telescopes in the Chilean Andes and at the South Pole will scan the sky, hunting for the tiny spectral distortions that could confirm the existence of decaying phantom particles or the explosive evaporation of primordial black holes. They are reading the fine print on the universe's birth certificate, looking for the signature of those early cosmic architects. Back on Earth, particle accelerators like the Large Hadron Collider and its planned successors are attempting to recreate the conditions of the first fractions of a second. By smashing particles together at nearly the speed of light, they hope to create and detect the exotic, supersymmetric particles that many theories predict. Finding a selectron or a squark would not just be a triumph for particle physics. It would provide a tangible candidate for the invisible matter that subtly tweaked the cosmic expansion rate and altered the final lithium yield. The search is a grand synthesis connecting the impossibly large scale of the cosmos with the infinitesimally small world of quantum physics. The solution to the lithium problem will not come from a single observation, but from a convergence of evidence. A new particle discovered in a collider, a specific distortion found in the microwave background, and a precise lithium measurement from a primordial gas cloud must all tell the same story. The mystery of the universe's first elements is no longer a static puzzle from the past. It is a living, breathing investigation, a cosmic detective story where we are finally assembling the tools to read all the clues. We have journeyed through 30 astonishing possibilities, from the bedrock of Big Bang nucleosynthesis to the fringes of electric universes and cosmic holograms. Each theory, whether grounded in established physics or soaring on wild speculation, represents a profound human effort to answer one of existence's oldest questions. This relentless pursuit is far more than an academic exercise. It is the fundamental engine driving cosmology and physics forward, forcing us to challenge our deepest assumptions about reality itself. The stubborn mismatch of a single element, lithium, has opened a window into realms of phantom particles, hidden dimensions, and cyclical bounces, proving that the smallest clues can lead to the grandest revelations. The mystery of the first 3 minutes is not yet solved, and the final chapter of this story will be written by the next generation of telescopes, colliders, and perhaps by you. The cosmos is a conversation, and your perspective is a vital part of it. Tell us in the comments which of these 30 theories captured your imagination. Was it the ghostly influence of neutrinos, the dramatic bounce of loop quantum cosmology, or the silent pull of a mirror universe? Let us know, and if this journey into the dawn of time sparked your curiosity, like this video and subscribe for more deep dives into the universe's greatest mysteries.